Okay, everyone. Today we'll be talking about a very important way to access our social media activities. Now, if you look at the past, we studied about the social media, rather platforms available out there. And last week we looked at authentication with social media accounts. So under that, we tried to use the social media as an authentication platform, meaning you might have an application, let's say e-commerce application or education application or news application, whatever it may be. Now, generally, you have a username and password for the application, right? So last week, we looked at using the existing social media account of the user in order to do the authentication. So that way, you don't need to remember another username and another password to log into the platform. So we also looked at different solutions. So starting from Facebook to Google to Microsoft 365 to Instagram, there's so many ways of logging in. And we also notice GitHub can be used, LinkedIn can be used. But you will not use everything everywhere, isn't it? You need to select what is relevant for something. Let's say, for example, if you're building an e-commerce site, no point having GitHub account or LinkedIn there. Probably Google or Facebook might do the trick. Whereas if you have, let's say, a platform for developers to come in for communication or collaboration or something, that case, you can probably use GitHub as a login mechanism, or even LinkedIn, because that's a professional account to come in there. So just because all the social media platforms available, don't bring everything to all the application, right? Not a good idea. So today we are trying to see another step of that, which is after you do the authentication, you have access to the social media account of the person, right? So normally you get the email address and the name of the person only. Now, what if you want to access more about this person who did the authentication through maybe Facebook or Google or LinkedIn, GitHub, whatever it may be, right? So you want more information. Like say, for example, if it is a GitHub account, you want to know all the projects he's working on, or maybe a summary of the commits and things like that. Or if it is a Facebook account, you want to find out his preferences. Maybe you want a picture of the person, things he likes, maybe. And sometimes you can go to the extent of finding out this person's friends also. So you have, let's say I log in using my Facebook account. This software application can look at my friends also. So through me, they can, download the list of my friends. And through those people, maybe they can also go to the next level. Now, we do have legal issues there. Is it good? Is it legal? Should we do that? Well, that's another matter. Now we are talking about the technical side of it. So technically, it is possible, right, to reach and get any information you want. So that's one thing. Number two, the question is, okay, how are we requesting this information and how are we getting this information? So if you have studied databases, generally speaking, databases, we use tables, records, and then relationships, isn't it? So these are called SQL type databases. So relational databases, that's the appropriate word. So these relational databases have tables, then tables have rows, and these rows have fields or columns. And we use essentially the select query, and then we can specify the table name. We can join tables. We can then apply filters. We can do things like unions, all kinds of stuff we do, but we are doing everything to a two-dimensional table, isn't it? So by joining, we get a 2D table, and then we apply the filters to this selected 2D table. That's what we do with relational databases. But there are instances where you can't represent certain relationships with using the relational 2D databases. You may need to go to a different direction. Like say, for example, coming back to my question of Facebook, you want to connect to Facebook, and then using the logged in user, let's say you want to go and find out his friends and how many people like video games, so how many people like reading, or how many people like the color blue, things like that. Or how many people who like color blue or color red, and then also like violent computer games. So you're trying to come up with a certain relationship of that nature. Well, by looking at it from the first instance, we might realize, okay, why can't we use 2D relational database to ask these questions? Maybe you can, but once you bring in few additional dimensions to the question, your database is going to be extremely slow, because some questions will require multiple queries. So you have one query, ask the questions, and then when you get the result, maybe you need to run another query inside that. So these are called query inside a query, right? So in a multi-query system, at one point your computer will run out of memory. That's what will happen. And also, since it's slow, either the hard disk or CPU might get into a lock condition, where one query is waiting for another query and this query is waiting for this query. So both the queries are waiting for each other. So there is something called a lock condition happening there. So we need a different way of thinking when it comes to complex queries, right? So that is where the graph database concept is coming into the picture. This is what we use with things like Microsoft 365, Facebook, even Google to inquire information from our database. Yes, you can use relational databases, but this gives you very fast and clean data sets coming out, because you don't need data that you are not going to use. So you can specify what kind of data you want and then have a very advanced queries to filter it out very well. Okay. So let's see how these things work. Now, what I'm presenting today is a very simple concept of how graph databases work. Uh, Now, to understand this, I've selected a very good free version called Neo4j. It's an excellent database out there when it comes to graph databases, and it's free. You can also run all kinds of queries. You can use it on with the Python, Laravel, JavaScript, Java, any language you want. You can use it very easily. There are libraries available for pretty much all the languages. So I'll show you a few things today in this presentation, essentially explaining the importance of graph databases. And I will upload an activity sheet where you can go through step by step and then get yourself familiarized with this system. Because later we'll be writing an application where we will be talking to a graph database and get the queries coming our way. So maybe we can connect with Facebook, maybe we can connect with, say, GitHub account, maybe to Gmail, or actually not Gmail, Google, and then inquiry some information. One of the most famous two places where we use graph databases is Facebook inquiries and also Microsoft 365 inquiries. Facebook, I guess we already know, so we can look at the things the user likes and also what his friends and others like. But when it comes to Microsoft account, this is a very common request. Now, for example, we might have a application where we need to record a calendar event. Yeah. Now, what if the user already has a Microsoft calendar? Or what if the user already has a Google calendar, right? So rather than you creating your own calendar, you can maintain a Google calendar or a Microsoft calendar. And then whenever the user adds something to the application, you just plug that back to their Google calendar. So if they're using an Android phone or Apple phone, whatever, they can see the calendar events on the phone itself without a special application. You can also pull information. Say, for example, you want to find out whether the person is free on Wednesday from 8 to 10. So then you can pull that information from Google Calendar and then check and see whether the time slot is free or available, and then act on your application, right? So that's why it's important to connect to these other external applications and pull information and also push information. So in all these instances, a graph database knowledge is very, very important. And in fact, it will make your life very easy also using graph databases rather than using relational database tables. Right. So what is a graph database? It is something that is designed to connect between the data, right? Well, that's the same thing we use relational database also, but here the connection between the data are considered as important as the data itself. That's the difference here. Now, generally in a normal MySQL, Oracle kind of databases, we assume the data as the most important thing. So we think the data is the most important, right? Whereas when it comes to graph database, we treat data as well as the connection between the data is also as very important. Now, we are not talking about the usual relationships here. We go a little beyond that, little advanced way of connecting data. Okay, now here's an example, a graph. Now you notice there are circles, then there are arrows, and there are some stuff on the arrow as well as inside the circle as well. So if you take, for example, film and session, or actually film and person, person likes film, and he also gives a rating. And then person is also booking, say, a film, right? Similarly, seat has a booking or booking has a seat, right? So all these are interconnected. Imagine trying to do this on a 2D relational database. It will be very, very difficult, isn't it? You will have lots of one to many, many to many connections between the tables. That way you can do it. But like I said, it will be exorbitant when it comes to resources. You will run out of memory when you run a complex query in a relational database. But on a graph database, it will be very easy and very less resource hungry. So a graph database is a type of database that uses graph structure, the one you just saw, right? For semantic queries. What do you mean by semantic queries? English-like queries, like just like SQL. It stores data in nodes, edges, and properties, allowing for a flexible and highly efficient way to represent and navigate relationships. So unlike traditional databases where the data is stored in the field, here the data is stored in nodes, edges, and also properties. Okay. Right. So if you look at the graph, I mean the diagram here, right? So you see the data is stored inside the node and also in these lines. These are called edges, right? Um, so everything is important here, right? So there are three co-components when it comes to graph databases: nodes, edges, and properties. All three are important equally. So node is the circle, we call it the entities or data points, like people, places, events, things like that. Edges are the connections, relationship or connection between the nodes. Properties are called the attributes or information about the node or the edge, right? So that's why if you notice here, here's a node, the circle, let's say a person is a node, and then this line is the edge. And on the line, we have attribute, right? It says likes. So three things are here. Three most important things are there. So why a graph database? Very efficient when it comes to handling relationships, right? Ideal for scenarios where relationships are as important as the data itself. Okay, so there are many places. You might think, okay, are there any places where relationship is not important? Well, yes, there are places where it's not complex. I can't say it's not important, but there are many situations where relationship is complicated, right? So 2D way of accessing might not be the way to go. Then comes the flexible schema. So your schema can be flexible. You can adapt to changes as you grow your chart. Now, this is not possible with our 2D table-based databases, isn't it? Once you design your table, that's it. You can't change. If you change, your code will also change. So we are stuck with the database structure on a traditional static databases. Then fast query performance. I told you, unlike the traditional 2D SQL setup where you will have a query inside another query, here it's very simple, very straightforward. So they are optimized for traversing. What does mean? What does it mean by traversing? Traversing means going from one node to multiple nodes, right? So you notice the diagram here. So if you start from, let's say, this node, I go from here to here, and then I have two roads. I can either go this way or this way, right? So, I mean, this is just one example. There may be so many similar connections as well. So it's very much optimized for traversing, meaning going from one node to multiple nodes, let's say from 1 to 100, 100 to 1,000, whatever. And then another very, very important one is the scalability. When it comes to enterprise level applications, scalability is a serious concern, right? How scalable the application is. So if you have a simple database, you can scale. There we will be looking at the storage size and then how fast we can access the database, right? In a traditional SQL type of MySQL type of database. But when it comes to graph databases, yeah, storage is also important. But then complex algorithm to get the data is already there in the database. So you don't need to do that much of processing in your application, right? So you can pass that processing onto the database. So it will be very fast and also scalable, as in there is no limit of table, field size, record size, whatnot here. So you just keep dumping data and connect the nodes and it will scale and scale and scale. So what are some of the example use cases where we can talk about or we can see the graph databases? First and foremost is social networks. Because when it comes to social networks, relationships are very, very integrated part of the social network, isn't it? In fact, it is the whole thing of social networks. So when I have a Facebook account, I go and let's say click some things to say, okay, I like, let's say cars, fast cars. Facebook will then look at who's close to me, let's say where I work, or where through my friends or through my office or through my other contacts and see who else can be connected to me. People who like cars like me. And then it'll suggest those people to me and say, look, these people also like cars. So maybe it'll say, okay, it'll show me those contacts on my dashboard when I log in first time, or rather when I log into my account as suggested friends. So how does Facebook know that I will like them? That is through relationship mapping. right? That's how also it finds out my long lost friends from school time or from my neighbors or my long lost friends. So it uses very sophisticated mapping technique to go from my account to my friend's account, from there to other friend's account, and then see, very complex way of figuring out who can be interconnected. Because more connections we have on the social network, it's profitable for Facebook. That is why they do it, right? And another very interesting area is recommendation engines, finding connections between products and users. So, as a very simple example, let's say I go to a e-commerce site and I'm buying something, right? Now, when I add that to my cart, it'll also at the bottom say people who bought this product also bought that product. Let's say I buy a laptop, it'll also say people who bought this laptop also bought this laptop case or keyboard cover or extra battery, something like that. So how does it recommend me these things? Again, through a very sophisticated linking of these nodes. And another very, very important aspect of graph database is fraud detection. What does that mean? Frauds happen in banks mostly with credit cards and accounting and things like that. Now, if you were watching the news last week, there were some 50, 60 people were arrested in Sri Lanka for cyber crimes. So they were sending fake messages to people and getting them on board and trying to get their OTP and account numbers and doing some transfer. They've been very successful doing that also, right? So how do you detect such cases? Well, you need to go through the relationships and then find out who's doing the hacking, right? So that can be detected through graph databases very easily. And the last one here is knowledge graph. If you look at how the knowledge is organized in libraries, right? So let's say you go to the library and say, look, I need a book on graph databases. The librarian may have not heard of this word before, but he will ask you a few questions. Okay, now what is it coming under? You'll say databases. Okay, so database is coming under what? You can say technology, or you can say IT. Okay, IT is coming under what? Maybe technology, right? Okay, that can be the root node technology. You will not list it under agriculture or food science or management, right? Maybe not. The main area can be technology, under that IT, under that databases, under that comes the graph databases. So then he will say, okay, go to room number 5, cabinet number 6, shelf number 3, and you will find the books there. Or if they have, library information management system might say, look, we had 3 books. These are the names of these 3 books. 2 is now taken by some people and 1 is available here. All right. So many different use cases when it comes to graph databases. Right. Now, here's an interesting slide where we are comparing our traditional relational database versus the graph database. Actually, there are 4 pillars when it comes to comparing. Number 1 is data model. So when it comes to the data model, under relational databases, we have tables with rows and columns, whereas graph has nodes, edges, and properties. And number 2 is schema, right? Relational databases have fixed schema, meaning once you create the database schema, you will never change it. Maybe you can do very slight modification here and there, but you need to go back and change the code also in that case. So it's a bit of a battle because if you change the database, you need to go and change the code as well. Whereas in the graph database, it's a flexible schema. You can change the schema at any time you want, no problem. And you don't need to change the code. Your code, most of the time, will not break. Just because you add additional data, your code will not break. Only thing is, if you remove data, then you will have to go and change the code, obviously, right? Third one is a query language. How are we talking to the database? When it comes to relational databases, it's generally speaking SQL. SQL stands for Structured Query Language. It's very English-like thing where you say select from this and that, join them together, filter it out, where the date is this, stuff like that. Very English-like language. Whereas Graph also has a similar thing. For example, Neo4j has a language called Cypher. Very simple, like SQL, English-like. Then there is Gremlin, SparkQL, and few things like that from various companies. The job there is to keep it as simple as possible. And the last is very important, performance, right? The relational databases are optimized for ACID transactions and join operations. Okay, so like atomic level connectivity and transactions, that's the whole point of relational databases. Whereas for graph databases, it is optimized for traversing and query relationships. So the biggest there in graph is relationships, whereas relational databases, the biggest thing is ACID and joins. Okay, so you see the difference there. Now, don't think that we can build our entire system with graph without using relational databases. Not really. If you look at large scale applications, you can see both of them. For some, let's say, simple data storage, you may use relational databases. Whereas if you think that there are many complex relationships, um, where you may have to go from one node to 100 nodes at once, stuff like that. In that case, you'll be using the graph database. Right, which brings us to a question of what are the databases available out there, the graph databases. Now, of course, there are expensive paid versions available as well. So I thought of looking at least few open source databases available. Now, although it says open source, there are also paid versions available. So you can use many of these things as a starting point to inquire, to get familiarized and things like that. But if you want to do a real world industrial strength application, well, then maybe you need to upgrade yourself into a paid package. So first in the line is Neo4j, one of the most popular graph databases. It's popular because it's scalable and also very fast performance-wise. And it also supports ACID transactions and offers a powerful query language called Cypher. Right? And it simplifies graph traversal and querying. A very, very good one. In fact, we'll be using it for our application as well. Second one is called Janus Graph. It's another distributed graph database. And again, it can handle large scale graphs, support various storage backends like Apache Cassandra and also Apache HBase, and also provide a flexible data model. Now, stuff like this may be required to handle, say, for example, if you're planning to have something like, say, Uber, very complex database, and getting data and relationship fast is very, very important. Or if you say, for example, Netflix, where you want to look at recommendations, people who watch this movie also watch those movies. People who don't like this type doesn't like that type, that kind of thing. So then ArengoDB is another multi-model database that support graph, document, key value pair. These are different types of databases, by the way, right? So far we only spoke about a graph and traditional databases. So this also offers a rich query language called AQL. So that's that. And then there is OrientDB. It's also called a hybrid graph. And it also supports ACID. Now, you see the word ACID. Just to remind you what is ACID, I'm sure you may have heard of this before. ACID stand for atomicity, consistency, isolation, and durability, right? Now, what does it mean? So atomicity is about the entire transaction take place at once, or it doesn't happen at all. If you take an ATM machine, for example, bank ATM machine, let's say I go and put my card in, I punch my number, my secret number, and I say, give me 5,000. Okay. And let's say I have 10,000 rupees in my account. So I'm taking 5,000. So look at the steps there. I put my card in. So the system verified my card. Done. Then I type my secret code. It verified my secret code. Done. Now I said, give me 5,000. That is also accepted. Done. And then it will go and deduct 5,000 rupees from my account. Done. So my balance is 5,000. The money still didn't come out of the machine, okay? But my 5,000 rupee deduction is done on my account. Imagine if there is a power failure now. Power goes off for a brief period and then the system goes down and then it comes back again. Now, what is the situation? My account says 5,000 rupees is the balance. But did the money come out? No. So the transaction is not complete. So I will have a serious problem explaining to the bank. The bank will look at the balance and say, look, no, you have only 5,000. You had 10,000 before the transaction. And now you have only 5,000. So money must have come from the machine. Maybe you are lying, right? So to stop situations like that, we use the atomicity principle where we start something called transaction and then we go through these steps. And once everything is successful, we'll close the transaction. So at any given moment, halfway through, if it breaks, if any of the step does not get completed, everything will be reversed. So the transaction stores your steps. So if, let's say, if a power failure happens, when it comes back, it knows the last step did not work, and then it will put my 5,000 back to my account, and then the transaction is reversed. So that is called atomicity. Consistency is about the consistency of the database, right? Now, there may be, let's say, a state of the database before the transaction and the state of the uh, database after the transaction. For example, the total balance of the money the bank has, let's say 1 million rupees, before I ask for 5,000. Now, after I take the 5,000, the bank balance should be, the entire bank's money balance should be 1 million minus 5,000 rupees, right? That is consistency. The third one is for isolation. That means now I am not the only person taking money from the bank, isn't it? There may be hundreds and thousands of people coming to various ATMs in the country and collecting money or depositing money. So my transaction, which I'm doing right now, should have no control or no activity to other people who are using the bank account, right? That is called isolation. So now durability is another very important one. That's the last one there. So this means if the system fails for some reason, like a power outage or whatever, if certain transaction was going on, it will be completed. Now, for example, I was trying to get the money and there was a power failure. So this reversing of my account must be happening, right? So that is durability, right? So those are the 4 principles when it comes to usual databases. And now, generally, we don't talk about, say, for example, the transaction systems in other databases. But when you see that the database is supporting ACID, that's actually very good. Yeah, because these are additional things that you can expect from a database. So Neo4j support ACID, and we can also see OrientDB also support ACID. And here is another list of open source graph databases. Vertiso, Kale, Stardog, dgraph, Agents Graph, all these things are available for us to use. Okay. Now, Virtuoso is using something called RDF datasets. And then Kale uses MongoDB also, right? If you want to, and it's written using Go. Now, this is a very important one because Go is a language for uh, multi-threaded applications, and MongoDB is another beautiful database for storing name value pairs. So, if your project requires high performance or high throughput data access, probably this might be the way to go, right? Of course, it's an architectural decision. We can't jump at things right now. So we need to do a very thorough analysis to understand which one is the best. Now, to help us with selecting the databases, I have a couple of pictures here. This one is about 5 boxes. All these are database applications, by the way. They are sorted according to the complexity of data. If you have the least complexity, very simple data, you can have key value pairs. So DynamoDB, Redis can be the simplest one. They give you amazingly fast access to your data, right? Say, for example, you want to store user a database, say user records like username, password, or something like that, very simple things. And you want very fast access to get to this. So, for example, you may be connecting your record to social media authentication. So every time you do a query or go from one page to another, it needs to hit the authentication system to see whether you're authenticated or not. So hitting the database very, very busy there. So you should get a very simple database with high throughput there. So Redis is the preferred one most of the time, but well, there are others also. Now the second one is called column family. These are used by very complex databases. Now, for example, and also search engines, let's say Google uses Cassandra to store large columns and large rows. So jumping to one or the other is simple, and then you need other heavy processor-based algorithm to go through the selected column or the row. Okay. Another famous one is Apache's HBase for large column-based systems. Then you have another type called the document databases. MongoDB is a famous one. Couchbase is another one, where document doesn't mean PDF document or anything, but we are talking about a record with lots of information, right? So let's say user record might have username, password, references, date of birth, school attended, all that stuff. So by storing here as a document database, you can also have it dynamically shrinking, growing, and stuff like that, right? Fourth one is the most famous one we've been using, relational or SQL databases. So there are so many tools available out there. MySQL, Postgres, DB2, Oracle, SQL Server from Microsoft, all those are coming under relational databases. And the last one, you see the complexity is also now coming from left to right. The last one is for the most complex data access, and Neo4j and DataStax are coming there as a very famous solution. We already saw, 9 or so solution, but there are other solutions as well. So this is a classification according to data complexity. Here's another way to do the classification. Now, these are all graph databases, okay? So here we only have 2. Here you can see a huge list, right? And also vendors or companies that are supporting the graph databases. AWS from Amazon, Neptune is a famous one. These are called semantic graphs. They follow something called the semantic standard. So there's a dgraph. There is also Cray supercomputers support this. NZgraph is another one. Then another classification can be property graphs. support label properties which cipher or proprietary languages. So this is where you can see Neo4j coming in. So there is Redis, another very famous one. Nebula is a famous also. So there is TigerGraph, MemGraph. So these are famous tools when it comes to property-based graphs. And then who are the big players supporting graph databases? One of the largest database, or rather, I would say one of the richest database companies out there was Oracle. And they also have their version of graph databases. Microsoft also has their tool Azure Cosmos DB. And in fact, Microsoft also has tools to talk to their traditional databases using the Graph API. And then SAP is one of the world's largest ERP manufacturers, ERP software manufacturers. They have Orient DB and also HANA as their different versions that support Graph. Because these software systems are very complex and people will ask all kinds of weird questions that require very complex relationships. So the system supports it there. Multimodal graphs support graph with APIs on top of NoSQL databases. So multimodals support more than graph, other things as well, right? So Janus is coming under that. Graph-based AI is another one. Terminus, Sparksy. So there are a few others there as well. So these are this is another way to classify our graph database world. There are so many solutions, so many companies jumping into this. Right. Now, so far, we looked at the theory. Let's look at an example. Okay. So I thought I'll compare a traditional table-based database and see whether we can understand the problem here, and then see whether we can solve this using a graph database. So we have a very simple table, 3 columns. We have name, we have the job, then we have the address. If you check this carefully, this is deliberately done this way. So there is a Sonia who is a pilot living in 101 in North Main Street. Then there is a Parker in the food service business. He also lives in 101. Maybe they are husband and wife. We don't know, right? The same address. But there's also Alex, another pilot. Sonia is a pilot, Alex is a pilot, but pilot Alex is living in another place, 455 West Avenue. Okay. Simple data set, right? A very realistic looking data set. So if you ask the question, where does Sonia live? Very simple question. Very simple to answer that question as well. So on a usual SQL, we'll say, go to the table and locate the name Sonia and name equals Sonia, right? So when we do the search, it will give us one record. So there is a person called Sonia, and then we'll get the record, name, job, address. Okay. We don't want the job. Maybe we can skip that. We can say only give me name and the address. And then immediately we have the address of Sonia. Simple, isn't it? Select all from contacts where name is Sonia. Rather than saying select all, I can say select name, comma, address from contacts where name equals Sonia. That can be my MySQL statement. And I'll get my record and I'm able to look at the address. So far, so good. Now, look at a second question. Who also lives at Sonia's address? Who also lives in Sonia's address? Now, that's a bit of a complex question. So first, we need to run our first query and see where Sonia is living, right? So we'll get that record. So then we need to look at the address and then see whether there are any other records in the address column. And we need to skip Sonia there and then look for other people in that place. So I have to run one query and then another query, isn't it? Query inside a query. So where we are looking for the name Sonia and also address 101 North Main Street. Okay. Now, do you see it's going both ways, isn't it? It start from Sonia and come to the address. It also locate the address and then go to the names. So when you do that, right, we will realize there are actually two records of the same address, and then we need to go back to the left-hand side to find the names. So let's look at it visually. To do this in a graph database, first of all, we will break down our data set into something called entities. Okay, so we have people, we have addresses, we have jobs, right? So people, there are three. There's Sonia, Parker, and Alex. Addresses are two, 101 North Main and then 455 West Avenue. Then we have server and a pilot, right? The server is in the food business, food service, and then we have pilot, right? So first step is to identify the nodes. Then we start putting these nodes, we rather connect these nodes together using the edges, right? And then we also write down the relationship. So we can say Parker, having the name Parker, has the address of 101 North Main Street, works at server. And if you notice the second one, look at that. Second layer from both. So 101 address, there are two people, isn't it? Now also look at the word written in full caps. Works as. Here there are two work as. Sonia and Alex both work as pilot. And here Parker and Sonia both has address of same. Right? So this is the next step. Basically drawing the relationship and also trying to have some clarity about how these things are getting connected. So putting the words like work as and has address is also important here. Okay, so we got our chart done. Now what? Remember our question? Who else is living at Sonia's address? So we first located Sonia, went through the has address, and then we found the address, which is 101. And then we do a reverse lookup of going from address to all the other nodes that are connected to the address. Okay. So this way, you notice how easy it is to locate Parker. We found Sonia's address, then we did a reverse lookup of has address thing to come to the other nodes. Right? So my objective today was to take you through graph databases, trying to understand what is it, where we can use it, some examples, and also to show you how to get it going with this. There are lots of examples, by the way, coming from Neo4j. What I'll do here is I'll share it with you so that you can do an example. So I'll be uploading the activity sheet soon. So check back the LMS for the activity sheet.